Today, I would like to talk about a novel energy storage system architecture called Reconfigurable Array of Inexpensive Battery Architecture, RABA. Hyperscale data center operators are now large consumers of electric energy and are under increasing pressures to adopt renewable energy. As a result, energy storage now becomes an integral component of a large-scale data center. Because battery-based energy storage is still quite expensive, there are basically two approaches to reduce this energy storage cost. One is to offer data center energy storage as a buffering service to electric grid operators. Second, one can try to build energy storage system out of cheaper batteries. For example, batteries that are retired from electric vehicles. This talk will focus on approach number 2. There are basically 3 pain points of using retired batteries to build energy storage system. First, if retired batteries are used, the electrical characteristics of the battery modules that make up an energy storage system become heterogeneous, which is unacceptable for conventional energy storage systems. Second, people are still concerned about the safety issue associated with the retired batteries. Third, even if the battery cost of an energy storage system can be reduced, the power conversion cost of an energy storage system remains significant, typically 30 to 40%. RABA is invented to address these 3 pain points. It uses reconfigurable inter-battery connectivity to accommodate heterogeneity of the battery modules. It supports accurate on-the-fly internal short circuit detection to address the safety concern. It enables the use of a variable number of batteries to produce AC outputs, as a result, cutting down the power conversion cost. So the key idea of RABA is to enable the inter-battery connectivity to be dynamically reconfigurable via software at the runtime. So why is this useful? Imagine that you have 3 batteries that are connected in series and the second one becomes bad. Traditionally, the entire serial chain becomes useless. But with RABA, you can bench the second battery and allow the first and third battery to continue work together. Or it can reduce unnecessary DC to DC conversion. For example, suppose you have 3 batteries connected in series, each of which has a voltage level of 3.2. And the required voltage level of the electric load is 6.2. In RABA, you can use only 2 batteries to satisfy this electric load. In traditional battery array, it is forced to use 3. And so it leads to unnecessary energy conversion and energy waste. It also can prevent unproductive balancing between parallel connected columns. For example, in this case, column 1 has 3 batteries with a total voltage level of 9, and column 2 has a total voltage level of 7. So with RABA, we can bench the entire column 2 and wait for column 1's voltage level to drop to 7 and let them connect in parallel. This eliminates unnecessary balancing between these 2 columns. So this is RABA 1's architecture. It has unparallel connected columns, each with M battery module connected in series. In this case, N equal to 4, M equal to 5. And it allows the entire column to be bypassed. And then each battery module could be enabled or bypassed with respect to its associated column through a enable bypass switch. The key hardware building block of RABA is this enable bypass switch, because it allows the transition between the enable and bypass mode while keeping the current going through each battery module constant. So this is constant current online switching circuit. So we build a special ASIC to enable this, to support this property. The time required to switch between the enable and bypass mode is very fast. So for example, from enable to bypass, it only takes about 30 microseconds and incurs an energy loss of 1.8 millijoule. Now, on the right, it shows the first commercial prototype of REBA. To evaluate its capability to accommodate heterogeneity of the battery modules inside it, we intentionally set the initial capacity of the battery module in it to a different value to simulate a certain degree of heterogeneity among the battery modules. And then we try two configurations. One is with a fixed inter-battery connectivity. The other is with reconfigurable inter-battery connectivity. And then we feed the electric load trace to the REBA prototype and measure four metrics. One is the total discharge service time of that electric load trace until the entire battery array stops working. And we also measure the total wasted energy storage when the battery array stops working and the standard deviation of the energy capacities of the battery modules in the array when the array stops working. And then the total number of transition between enable and bypass when the inter-battery connectivity is reconfigurable. In this table, each entry has two values, one corresponding to fixed inter-battery connectivity, the other corresponds to reconfigurable inter-battery connectivity. Now, for one particular workload data center, the total discharge service time improves by 84% from 4.16 hours for fixed connectivity to 7.66 hours for reconfigurable connectivity. The reason that the service time is increased so much is because you reduce the total wasted capacity by more than 96%. Now, the following slide will illustrate why this is the case. On the left, you have this fixed connectivity situation. So all the batteries start with a different initial capacity, and the rate of decrease are almost the same. So the entire battery array stops working when the capacity of the weakest battery is exhausted, right? And so that's fixed connectivity. Whereas in the case of REBA, they all started with a different initial capacity, but the rate of decrease is different because REBA trying to balance the capacity of the battery module as it serves the electric load. So sometimes some batteries are enabled when the lights are green, and sometimes they are bypassed when the lights are black, right? So in the end, the capacity of all the batteries are exhausted almost at the same time. This is the trick why REBA is able to squeeze the last bit of juice from every battery. Now, traditionally, if you want to build an energy storage system, you need a battery array coupled with a power conversion system that converts it DC to AC. We improved REBA 1 to form REBA 2 in order to cut down this power conversion cost. So the idea is that the last battery module of every column of REBA is now associated with a programmable switching regulator rather than an enable bypass switch. This switching regulator allows the attached battery module to contribute a fractional amount of its capacity to the service of a particular electric load. So for example, assuming that every battery here has a voltage level 1, and somehow we want to produce a AC curve. So at a certain point, we need an output of 1.2 volt. We can enable one of the battery and then use the battery 5 to produce 0.2. Or sometimes we need 2.3, then we can enable 2 batteries and then ask the B5 to produce 0.3 and so on. So with this kind of mechanism, a variable number of batteries are used to produce a particular output of the AC curve. We can significantly reduce the power conversion cost. In summary, REBA is designed to enable lower cost, heterogeneous or retired battery to be used in constructing cost-effective energy storage systems. In fact, this reconfigurable inter-battery connectivity enables virtualization of battery resource the same way as we do for virtualization for compute or storage resources. The unique features of REBA are a reconfigurable battery array architecture to accommodate heterogeneity among the battery modules, a distributed multi-level inverter architecture that can significantly reduce the power conversion cost, and then an on-the-fly internal short circuit detection algorithm that addresses the safety concerns of retired batteries. Thank you.